And a little bit of recap so that we can continue where we left off last time. Okay. So what is peak resolution? Simply, when we say resolution, what does that mean? Okay, Drew? The separation of two peaks. 2 or 3 or 4, depending on how much. So resolution, it's how they resolve from each other, how you can separate them from each other. So you have a mixture of 2 or 3 or 4, how much you can get separation. What is a solvent front? All of you experienced that today. What?
It's basically the clearing out of the void volume, and then you solve the peak, which means your experiment's actually getting through.
Yes. So the void volume, so once from the time of injection to the time where the solvent hits the detector, that's the void volume. And then when the solvent hits the detector, the detector recognizes the solvent. So it gives you a hiccup. It tells you, hi, solvent, there's a peak that shows up. Okay, what is the difference between retention volume and retention time? Is there a difference? What's retention volume then? Yes? It's the volume of the solvent that it takes for a solute to leave the column to get detected. Yes. And then the retention, so it's basically retention, how long it took on the column, how much volume it needed to get it out of the column. And the retention time is the same thing, but here the unit is time, how long in time it took for the solute to leave the column. So you can either record retention by volume or retention by time, but often it's reported by retention time. What is the relationship between peak width and resolution? Yes, Jenny.
Wider peak is less resolution.
Yes, so the wider the peak gets, the broader the peak gets, that means you don't have good resolution. Because to illustrate, so if you have two peaks, if they are sharp peaks, they are well resolved from each other. But as the efficiency of the column is reduced, so you can have really nice sharp peaks separated by less than a minute, by 0.5 seconds. But then if you lose resolution, they're going to turn out like that, and then you'll have a double peak or a split peak. What is the first step in developing a separation between solutes of interest in your sample? So you have a mixture of, like we said last time, carotenoids, and you want to separate them. What's the first thing you want to do?
See if there's an SOP.
Yes. See if your lab has a standard operating procedure, and if not, what do? Go to literature. And are we always sure that the literature method is going to work? No. But we try it, and we modify it from there. It's almost everything you want to analyze that somebody had done it before you, almost every time. So, but it doesn't necessarily going to work for you because you have a different system, different columns, different operator. So you have to adjust based on your own parameters. Okay, so we're going to continue with resolution from here. So I'm going to step back just to remind you of this equation. We talked about resolution being dependent on 3 factors. One is efficiency, selectivity, and capacity. We're going to talk about each one individually. So efficiency has to do with number of theoretical plates, n value, and we're going to talk about that. Selectivity has to do with the alpha, which is the separation coefficient. And then capacity, it has to do with the retention time of that particular peak, and we're going to talk about that itself. So you have A, B, and C. We're going to start with A. So have you heard the term of number of theoretical plates before, Vaidi? You did? So what the? You have a question? Yeah.
If it's a double peak, how will we plug in the value for W2 plus W1 for calculating resolution?
Okay, so, well, usually what you want to do is, there is a way in integration where there will be a dotted line. Let me show you. But usually you don't do that. You try to work on your resolution to enhance separation. It's very hard to integrate when you have a peak that looks like that. It's really hard to integrate. So what the software tries to do is do this kind of integration for you, but this is not accurate. Okay? So you want to try to separate them. But if you want to do that, then this would be your theoretical peak, assuming that you have a Caucasian kind of peak, like a hill-shaped peak, not tailing. Sometimes the peak tails. So it's not always accurate. So you need to have good separation in order to get the accurate width of your peak.
How does the value actually signify?
What?
How, if resolution, if the value is like high, what does it signify? If the resolution is low, what does it signify? Say resolution is say pi or something, or resolution is point. It doesn't signify anything. So what is the point of
It
calculating?
is specific, the resolution changes with your method. So sometimes your resolution is 0.5, but you have good separation. Sometimes it's 5 and you have good separation. It depends how close your solutes are to each other. So every time we want to compare with the same, like you would run a sample and you would run it after 100 injections and you see how that particular sample changes. That's how you determine your efficiency. Okay, so you have to run the same thing over time, so the column deteriorates over time. So you would run, let's say, your standard, and after 300 injections, you run the same standard and see if there's a change in resolution. Okay, because the resolution is specific based on you have your retention time, you have your column dimensions, you have your different solutes interactions with the column, so it's not a constant number for anything. Yeah, good. But good question. Okay, so number of theoretical plates. Have you heard this term before? Or if you heard it, you forgot it. It's just an annoying term that everybody forgets. But it's called theoretical because it's an imaginary. You try to understand equilibrium by thinking that your column is divided into segments. So let's say you have your column, and you run, let's go with caffeine. You've done, some of you did caffeine today. And you run caffeine, and then your caffeine goes through a series of equilibrium. There's your mobile phase. And then your solute is equilibrating and moving down with your mobile phase and equilibrating again, until it comes out as a single peak. Sharp and nice. You have a sharp peak, that means good resolution. All right, and then your column is about a year old. So something has happened to the efficiency of the column, it deteriorated. So what happens after a period of time, the equilibration, it should be the same dimension, I don't know why I went wider, but the same sample you run, same caffeine you run, it takes longer time to equilibrate. So when your peak, so your solute here is staying equilibrating over a broader area on your column. It's diffusing within your column rather than going in and out. So what happens is you get a peak that is broad instead of this nice sharp peak. Okay? So your number of theoretical plates, this is a theoretical plate, over time what happens to it? Decreases. So that's reduction in the efficiency of the column. The same, you have caffeine. The same compound you run in your column when it's new versus a year old, you start with this shape of a column of a peak, you end up with this peak. Why? Because your sample now is spreading. Instead of moving as a sharp, going from a low concentration to high concentration, but not diffusing within the column, going in and out as a sharp band and giving you a sharp peak, here is just diffusing within the column and coming out as a sharp, as a non-sharp, a wide peak. It's diffusing more, spending more time in the column, taking longer to equilibrate between the mobile phase and the stationary phase. So it is inversely proportional to the width of your peak, and also it is directly proportional to the retention time. So the longer the retention time, the higher is the number of resolution. The shorter the retention time, that means it's not retaining long enough on the column. It's just coming out sooner. Let's say this 15 minutes, it came out here at 9 minutes and then became broader. You're not having enough binding or good binding. So it is this efficiency or this number of theoretical plate is affected by several factors. We're going to talk about that. Any questions about yes?
For this, is there a standard you can run to see how, basically how much your column's holding up over time?
Yeah.
See how many plates you
Yes. Like this example, I gave you caffeine as you used it as a standard. You can choose whatever you want. When the column is new, you can say, I'm going to test this column with this standard every time. And then you monitor it over time to determine how you lost efficiency or not. Okay. So
the number is inversely proportional to the width of the peak.
yes, because here if the width, when the width is bigger, that means your n number of theoretical plate is lower. Okay. So number of theoretical plates are directly proportional to the length of your column. Okay, so if you have a shorter column, you'll have less number of theoretical plates. If you have longer column, you'll have more number of theoretical plates. And the longer the column, the better is the resolution. Okay, so but if you want to look at the column efficiency, not considering the height of the column, you calculate something called height equivalent to theoretical plate. So the height equivalent to theoretical plate is basically the length of your column divided by the number of theoretical plate. Then you get the length or the height of an individual theoretical plate. And again, for each column, for each solute, you have a different height equivalent of theoretical plate. So if you're running caffeine or if you're running another phytochemical of a particular class, they will have a different height equivalent theoretical plate. It's not a constant for each for solutes. It's for each solute they will have their own height equivalent of theoretical plate. So the height equivalent of a theoretical plate, so the height of each equilibrium section is influenced by 3 factors. Okay, so you have factor A, which is called eddy diffusion. You have factor B, which is longitudinal diffusion, and factor C is mass transfer. So eddy diffusion, longitudinal diffusion, and mass transfer, and the mu here is your flow rate. Okay, so let's look at eddy diffusion. So if you have, let's say, a river with large rocks, and then you have a river with really tiny pebbles. So you have a pebble here and a large rock here. And you have a river flowing over these rocks. If you have a large rock, your flow of the river, of the water, is going to have multiple, they will take multiple directions. They're going to stumble over the rock. One will go that direction, one will go that direction. A stream will go that direction. So your stream is going to be divided, and then therefore your solutes are going to be divided and not travel closely to each other. However, when you have small pebbles, your stream is not going to be really interrupted as much by the pebbles. So they're not going to, the small pebbles is not going to redirect your stream. So your solute are not going to be directed in so many different directions. So this will generate a really sharp band. This is going to generate a large band because they're going into so many different directions. They're spreading out rather than traveling together in a sharp band. So this is going to give you a sharp peak. This is going to give you a broad peak. So that's eddy diffusion. So basically, the height, as the eddy diffusion increase, the height of a theoretical plate will increase, the resolution will decrease. So basically, the way to control that is to get a packing material that has small particle size. So you select your silica or whatever material you have in your column, you select to have a very small particle size to reduce the effect of A. Okay, good. Moving on to B. So B is called the longitudinal diffusion. So you have a peak, a band that starts here. So your sample is going from concentrated to less concentrated, and then there's your mobile phase flowing. So you have a movement in and out, and then you have a longitudinal movement going from a diffusion. You're going from a high concentration to low concentration. So it's going to move downward like that, moving from high to low, and so on. Now, what will make this longitudinal diffusion wider is if you have a very low flow rate. That's why it's affected by the flow rate. Here, it's in the denominator. So if the flow rate is high, this B value will be low. If the flow rate is low, like here, if looking at here, if flow rate is low, your height of theoretical plate will be high. So we want to make sure not to choose a flow rate that will result in a lot of longitudinal diffusion rather than in and out of the stationary phase into the mobile phase. So flow rate here plays a role. Another important factor where flow rate plays an opposite role is the mass transfer. The mass transfer is between here and here. How long it takes to reach equilibrium. How fast your solute is moving in and out and reaching equilibrium. Okay? So the higher the flow rate, the faster you're going to reach equilibrium. But again, there is an optimum. If your flow rate is way high, what's going to happen is you don't have enough time for equilibration, then you don't get good separation. So it has an opposite effect. So there's always, you need to find your sweet spot in terms of flow rate. You don't want it to be too slow, and you don't want it to be too high either. You want to find that perfect spot of a flow rate, and that happens with experimentation. You cannot just guess it, to figure out what flow rate will give me the smallest height equivalent of theoretical plate. That means you will have the sharpest peak. Okay, so you have mass transfer, longitudinal diffusion, and eddy diffusion. All impact your resolution. Okay? Any question? Okay, I guess chromatography is going to continue on till Wednesday. All right.